Last year you learned about atomic structure, up until about the Bohr model, which describes an atom as having a nucleus in the center which has protons and neutrons, and having shells with electrons circling around it. This is a fairly simplified model of an atom, and you probably got to the stage where you knew about the certain levels. So there are several levels which we called n equals 1, n equals 2, n equals 3, those sorts of levels. And for each of those levels, there would be a certain number of electrons associated. So for n equals 1, there was 2 electrons. n equals 2, there was 8 electrons. n equals 3, well, there's actually 18, but in the outermost level, there was 8 electrons again. So you had this 2, 8, 8, and then I think 18. You had that sequence that you had to remember as a number of electrons in each orbital that made a complete orbital. Transitions between these various levels require energy, and these transitions can be seen in atomic emission spectra or atomic absorption spectra. You may also recall this sequence describes the number of electrons in the valence shell of an electron. But the reality is a lot more complex. Describing these levels as shells is really quite misleading. In actual fact, the position of an electron is best described by a probability distribution or a wave function. This is really the basis of the Schrödinger model of the atom, which requires 4 quantum numbers to solve the wave function. And these quantum numbers are listed below. N is the principal quantum number, and it's assigned 1, 2, 3, 4, any number, any whole number. For the most part, this is equivalent to the period in the periodic table. L is the angular momentum quantum number, which is 0 for n equals 1 or 0 and 1 for n equals 2. So it's basically n minus 1 and 0, 1 up to n minus 1. In chemistry, we actually describe this by letters S, P, D, and F, and these describe the shape of the orbital. Within each suborbital, there is also a magnetic quantum number, ML, which describes the orientation of an electron in space. So you can see that ML has the same number, L, but also plus or minus 1 here. So its ML is minus L, 0, plus L. So in the case of 2, it's minus 1, 0, plus 1. In the case of 3, it's minus 2, minus 1, 0, plus 1, plus 2. So you can see that for the P shell, there are 3 orientations that are possible. The last quantum number is ms, or the electron spin, which can be plus a half or minus a half. And this is actually the orientation of the electron spin. In chemistry, we describe it as spin up or spin down. And the Pauli exclusion principle actually states that no 2 electrons can have the same set of 4 quantum numbers. And this really implies that there's always a spin up and a spin down, never a spin up, or never a spin down in the same energy level. What this means is that for the P shell, there are 3 various orientations, and within each of those orientations, there is a spin up and a spin down possibility. So there's 6 different possibilities. So when you add up all the possibilities in these n equals 2 level, you can see that it's 8, which means you get those numbers that we started with last year, 2, 8, 18. Using just these 4 quantum numbers, we can describe the electron's position, shape, orientation, and spin. But what does it actually look like? Let's have a look at the diagrams. This is a diagram of the actual electron's position. Now remember, we're talking a probability distribution. So we're not saying this is exactly where it is. This is probably where it is. The S level is a spherical distribution. The P level is what we describe as perpendicular. And you can see that it's either perpendicular along the x-axis, the y-axis, or the z-axis. And because there's 2 different orientations, you've got a plus or a minus, so a spin up or a spin down. So there are 6 possibilities for the P. For the D orbitals, we're talking about diagonal. There are no d orbitals that correspond to that principal quantum level n equals 1 or n equals 2. The first d orbitals actually occur when n equals 3. So the 5 3D orbitals are shown in this diagram. The d orbitals have two different fundamental shapes. 4 of the orbitals, dxz, dyz, and dxy, and dx squared minus y squared, have 4 lobes that are centered in the plane, indicated in the orbital label. Note that the dxy and the dx squared minus y squared are both centered in the xy plane. However, the lobes of the dx squared minus y squared lie along the x and y axis, while the lobes of the dxy lie between the axes. The fifth orbital, dz squared, has a unique shape with 2 lobes along the z-axis and a belt centered in the xy plane. The d orbitals for levels of n greater than 3 look much like these 3D orbitals, but with larger lobes. To describe the electron configuration of an element in its ground state, we use a set of rules. The first rule is the Aufbau principle, which in German basically means build up. And that basically means you add an electron at a time, starting from the lowest energy until all of the electrons have been placed in the appropriate orbitals. Hund's rule is the second rule that we'd use. And when it's a similar sort of thing to the Aufbau principle, you're starting from the ground up using the lowest energy. But the important point is that the lowest energy is where there is the maximum number of unpaired electrons. The last one is the Pauli exclusion principle, which we described before as having the spin up and the spin down state. Let's give an example for this. Carbon. It has 6 electrons, and it will start with the lowest possible electron. So we're going to have 1, n equals 1, spherical orbit, 2 electrons. N equals 2, spherical orbit, 2 electrons. That's 4. Now we've got n equals 2, perpendicular, and there's 2 electrons left over. So we've got 2 describing it in that way. What that actually looks like is slightly different. There's a different notation we can use. In chemistry, it's slightly easier. 1, 2s, and 2p, and we use boxes. Boxes are useful. So the s orbitals have just single boxes, the p have 3. And that's the different orientations. So the spherical one, we start with 1s1, 1s2, spin up, spin down, 2s1, 2s2, 2p1, 2p2. So you can see for carbon, we've used this second rule, Hund's rule, and we've put both our spin states up. Another example, say oxygen. It has 8 electrons. So same thing, 1s2, 2s2, we'll go for 2p4. Similar sort of principle applies. We have spin up, spin down, spin up, spin down. But when we get to the state here, we start with 1, 2, 3 spin ups. The fourth one, where does it go? It has to go here. So spin down. This is our building it up from the lowest energy level. There are sometimes variations to the filling order, which are due to overlapping energy levels, but in general we can fill using these rules. A diagrammatic way of remembering it is shown here in this diagram. In this case, the rule is basically you start from the 1s2, 2s2, 2p6, 3s2, p6, 4s2, 3d. You can see that the order follows through. Now, it's not an order where you always have 1, 2, 3, 4. You can see that sometimes you have 3 after you have 4, and sometimes you have 4 after you have 5, not the other way around. And this is due to the energy levels. So you can use this diagram. I find it actually much more preferable to use the periodic table because the periodic table actually shows you a lot more information and gives you that same filling order. You can see that the s orbitals are in the alkali and alkali earth. That's group 1 and group 2. The p orbitals are in group 3 to group 8. So the noble gases, the halogens, and the carbon, nitrogen, oxygen type materials. The d orbitals are all transition elements, and the F is the lanthanides and the actinides. And the key in the filling sequence is that when n equals 4, we start with 4s1, 4s2, and then we get into the transition elements. So we actually go to 3d. So we have 3d1, 3d2, all the way up to 3d10, and then 4p. So go back to the p. And same thing with the 5s. And then when you get to the 6, you end up with lanthanide, so you get 6s2, 5d1, so you start filling that 5 orbital, but then you go into the f orbitals. You fill up the f orbitals, and you start from F1, 4F1 through to 4F14, and that fills them up completely. And then you go back and fill up the 5Ds before filling up the 6Ps. And that follows that same order, but it's written in the periodic table. And the same thing happens for when n equals 7. So what does all this mean? The electron configuration actually gives rise to several of the properties of the periodic table. For example, ionisation energy. If you have a look at ionisation energy, you can see that it increases across a period and decreases down a group. This can be seen more clearly in the graph. You can see that there is an immediate increase across a period and a decrease down a group. These changes are purely due to changes in electron configuration. When you start at a noble gas and you remove an electron, which is what ionisation energy is, then you have a complete shell which is now slightly unfilled, so it takes a rather large amount of energy to remove it. When you have an unfilled shell, less energy. And you can see that there are variations in this graph, which are purely due to the changes in electron configuration. I find it slightly easier to actually visualize it using color. If you use the color version, you can see that there is a change across the periodic table. Plus, you can see the change as you get into the p orbitals. You can see the change between zinc and gadolinium is purely due to the change in p orbitals and the d orbitals here, the differences in energy levels. The electron configuration also can describe changes in atomic radii. Now, the atomic radius decreases across a period and increases down a group. This is due to two reasons. The increase down a group is purely due to the increase in the principal quantum number. The first group has one shell, second group has two shells, third group has three shells. When you're looking at the decrease across a period, however, there's the suborbitals that is changing here. So the decrease there is due to two factors. One is when you have more electrons, you have actually a greater affinity of those electrons to the nucleus. As you add more electrons, you also add more protons. But also, the shielding decreases that effect. So you're getting a decrease in the atomic radius across the period and an increase down the group. These electron configurations can also predict various things like valencies and also reactivity, which are purely due to the changes in electron configuration.